Okay, in today's topic, we will discuss how to process n jobs through m machines. Okay, as the problem suggests, there will be total number of n jobs that will be denoted either by some numbers or some alphabets and so on. Okay, usually you will find that the jobs are represented by numbers 1, 2, 3 up to n, which is supposed to be performed on m number of machines, and the alphabets are used for representing the machines. In some examples, I have seen even numbers are given to the machines. Okay, so don't get confused with the numbers, the denoted values, whether it is a numerical value or alphabets. Please check what it is given. And it can also happen that instead of giving the machines on the rows and the columns as the jobs, they might give it the other way around. So you have to rearrange the whole problem properly. Okay. So this is just for your information. Okay. The problem, as I said, will have n jobs denoted by 1, 2, 3. It is not a rule that it has to be denoted by 1, 2, 3. Secondly, each job is to be processed through m machines. Here we say like we are using the alphabets A, B, C up to m. Okay, and the order is also in the same sequence, A, B, C up to M. If the order is given in some, different sequence, please make use of that as well. Secondly, there is no passing of jobs is permitted because you cannot skip any of the jobs here or the machines. Okay, so no passing of jobs is permitted. Same order of job is to be maintained for each machine. Okay, these are some of the assumptions. The expected processing time is given in this table form like this. Now, as you can see, the jobs are represented as 1, 2, 3, 4. Sometimes you'll find that the jobs are given on this side here, along the rows, in the first column, and here we get the machines. So in such cases, please rearrange the whole problem and then solve the problem. Okay, and the main purpose, as you know, the main objective is to find the optimum sequence of the n jobs that should help me minimize the total elapsed time. Okay, and we are also going to calculate the idle time for each machines. That is the whole purpose. Now, what are the methods which I'll be using? We are going to again make use of the same Johnson's rule and the extended Johnson rule for more than 2 machines. Last time we saw the extended Johnson rule for 3 machines. Let us see what we can do in m number of machines. Okay. First of all, we have to identify the smallest processing time on machine A to M, A and M, sorry, and also find the largest processing time on each of the remaining machines in between. So the first machine and the last machine which is there, we have to identify the smallest processing time, and all the remaining machines between the first one and the last one, we are going to find out the largest processing time. Clear? This is my first step. Then check out if the first condition is if the smallest processing time on machine A, if it is greater than the largest processing time on each of the machines B, C up to L, okay, and not M. That means the maximum of, you can say the largest processing time on all the machines except for the last machine, if that is smaller than the smallest processing time on the machine A, then we can go ahead and solve this problem further. Okay, that means we can apply the Johnson's rule. Otherwise, it is not possible. The second rule as well. So either this number one or number two should be satisfied. In this case, we look at the last machine, that is the smallest processing time on the last machine, machine number M here. If that is greater than the largest processing time on each of the machines, B, C up to L. Okay. Now, here there's a problem. Yeah, fine. This is okay. So the last machine, if the smallest processing time on the last machine is greater than the largest processing time on the machines in between other than the first machine, then we say it satisfies the condition. So either one of the condition or both the conditions can be satisfied. If it is not, then you cannot go ahead and apply the Johnson's rule to solve this problem. Okay, and it cannot be, you can say solved. Fine. If either one of them is satisfied, okay, we can go ahead to step number 4. What is the step number 4 here? We have to convert the M machine problem into an equivalent 2 machine problem by introducing two fictitious machines X and Y with corresponding processing time defined as. Now here I have mentioned X and Y. It is not necessary that you name the machines as X and Y. If you want, you can give some other names as well, okay, provided that name is not a part of the problem given to you. Is this clear? Now, what are the processing time for this fictitious two machines? Your xi will be used as ai plus bi up to li. So the summation of, or the addition, sum of all the machines from a to m minus 1, that is leaving the last one, all that processing time together will give me the processing time for xi, okay, where the value of I is going to move from 1 to m. Whereas for y, leaving the first machine, okay, leaving the first machine, for the second fictitious machine, I'm going to add the processing time from b up to m. Clear? Now, once we get this two machine problem, we can apply the Johnson rule, which we did in the first example as well. What is the Johnson rule? Finding the minimum processing time, okay, between these two fictitious machines. If the minimum time or processing time belongs to the first machine, okay, we assign that particular job at the beginning of the sequence. Okay, at the beginning also, depending on the slot which is available. If the minimum time is of the second machine, I assign that particular job at the end of the sequence. Clear? If there is a tie between both and both lies on two different machines, then it is up to you to decide which one you are going to take. Whether you are going to put it at the beginning or at the end, it hardly makes any difference. Similarly, when it is two different jobs, okay, and two different machines, then the one which is on the first machine will go at the beginning, and the other one which is on the second machine will go at the end. That is how you are going to apply the rule. Okay, let us take an example. So here I have an example of, say, how many 4 machines jobs we have and 5 machines we have. So we have to find the optimal sequence for the following sequence problem of 4 jobs and 5 machines. When passing is not allowed, okay, you cannot skip, you have to go in the same sequence, of which the processing time in hours is given below. Okay, the sequence is not mentioned here. We'll take the same sequence as A, B, C, depending on what is given to us. Okay, now in this example which is given, if you look at the problem, okay, the jobs are mentioned, okay, along the first column, and the machines are in the columns, right? So we have machines A, B, C, D, and E, and we have job 1, 2, 3, and 4. Okay, actually this has to be rearranged so that I can put 1, 2, 3, 4 jobs as the column headings and the machines along the, you can say, row or row heading, you can call it. Okay, now how do I check what is the first step? As I said, the first step is to find the smallest processing time on the first machine and the last machine. So what is the smallest processing time on the first machine? Machine number A, it is 5. Okay, what about E? It is 6. So we have the smallest value for A as 5, which is of A3. And for the last machine, that is machine number E, the smallest processing time is 6, which is for E4. Okay, what about the other machines in between the first and the last machine? We are going to find out the largest processing time. Okay, so for the largest processing time for machine B is 6, which is of B2. Then for C, it is 5, which is C5. And for D, it is again 6, which is of D3. Okay. Now, using these values, we are going to check the condition. What is the condition? Minimum of, let us consider the first machine. So minimum of the machine A should be greater than or equal to maximum of the three machines B, C, and D. Okay, so maximum of 6, 5, and 6 is 6. Minimum of A is 5, so which is not greater than, neither it is equal to 6. Okay, so the first condition is not satisfied. Let us check the second condition. What is the minimum of E? It is 6. Okay, and the maximum between B, C, and D, that is 6, 5, and 6 is 6, which is equal to 6. So the second condition is getting satisfied. That means I can go further and change this problem into a equivalent two machine problem and then solve it using the Johnson's rule. I hope I have made everything clear. Any doubt here? Fine. Let me show you the problem. Solution. Now, you by chance I have, okay, this is what I explained you. Okay, the first one here we have seen the minimum of AI is not greater than equal to max of BI, CI, and DI. Okay, but however, the minimum of EI is greater than equal to max of BI, CI, and DI. And what is the max of BI, CI, and DI? That is between 6, 5, and 6. 6 is the maximum. Okay, and as it is equal here, we can go ahead and solve this problem using the, you can say, the Johnson's rule. But before that, before applying the Johnson's rule, we have to convert this problem into an equivalent two machine problem. Okay, so let us do that conversion. And as you already are aware, it is simple calculation. I'm going to include two machines, X and Y. Okay, and now I'm going to put the machines along the, you can say, rows, and the columns will be having the jobs 1, 2, 3, 4. So I have to rearrange this like this. So we have the first value as 17, where we are adding the values of A, B, C, and D. We are not including E to get the value for X. Then for the second machine, it is 6 plus 6 plus 4 plus 5, and so on. For the second machine, that is for Y, we are going to ignore the first machine and make use of the values of B, C, D, and E. Okay, and add it up and get the processing time for the fictitious machine Y. Any doubts here? Fine. Let's go ahead. Now, once we get this machine, this is my table for finding the optimal sequence. Okay, there's a question. Let me answer this first. Okay, so how to make the table? Step 4. How to make the table? Okay, coming back. So step number 4. Let me go back. Okay, see, here we are including two fictitious machines, X and Y. I have already mentioned the formula. Okay, is for the processing time for Xi, let us say X1 for this machine, for job 1. The value of A1 plus B1 plus C1 plus D1 will be the new processing time for this machine X. Okay, here we are ignoring the last machine. Whereas when we do the calculation for the second machine, we are ignoring the first machine, that is A, and only using B, C, D, and E. Okay, so these values are coming from this table here. Where's the table gone? Here it is. Okay, so when I'm finding the value for, say, the X machine, I'm going to use 7 plus 5 plus 2 plus 3. Ignore 9. Okay. Similarly, we can do for the second job, the third job, and the fourth job, where I'm ignoring this column here, the machine number E. When we are doing the calculation for the second machine, the second fictitious machine, I have to ignore the first machine, okay, and use the values from 5 to 9, that is B, C, D, and E. So 5 plus 2 plus 3 plus 9 will give me the value for the first job on machine number Y. I hope I have made this clear. So this was the machine, the value which we got. Okay. Now, once we get this, as I said, we have to create another table where we are going to find the optimum solution. So we have got this table here. Okay. And I have put the jobs as 1, 2, 3, 4 along the column, and the processing time, corresponding processing time on the machines X and Y. The order of assignment and the optimal sequence. Now, this is just a very simple one because we have only 4 jobs here. First of all, find the minimum value. Which is the minimum value here? 14 is the minimum value. Okay, that means the order of assignment will be done for this particular job first. So I'll put 1 here. Okay, now look at the minimum value, whether it is on X or Y, whether it is the first machine or the second machine. If it is the second machine, then put it at the end of the sequence. Okay, so this will be 1, and because it is 14, the second machine, the fourth job will come here, right? Ignore this fourth job and now consider the first 3 jobs to find the minimum value. The minimum value is 17 here, and it is on the first machine. Okay, so second order of assignment will be here. And because we have a slot available here at the beginning, so this will be my first sequence. So I'll come here. Ignore the first job and the fourth job. Look at the values which we have for the second and the third job. Minimum is 20, okay, which is on the first machine. So the third order of assignment will happen on this machine here. Okay, and because this is on the first machine, it will be at the placed at the beginning. Okay, at the beginning of the sequence, in the slot which is available, not here, but after 1. Okay, so it will come here. So 3 will come here. Okay, and we have only 1 left. So 2 is going to go at the end here. And this is my optimal sequence, or the optimum sequence through which I can run my jobs on the machines X, Y, and as well as the machines A, B, C, D, E. Okay, so the sequence which we get using this fictitious machine X and Y is applicable to the original problem where we have 5 machines A, B, C, D, and E. Okay, so the optimal solution for this machine will be 1, okay, 3, 2, and 4. Now arrange this to find out the total elapsed time and the idle time for all the machines. Okay, in some cases, the idle time is calculated later, but I have put it in the table itself so that it becomes easy for me to calculate and even easy for you to understand it. Okay, so I've created a table like this. Now you have to go through this now. I'll just explain you the first 2 lines. Okay, now as you know, the first job, this is my optimal sequence, 1, 3, 2, and 4. For each machine up to E, I have the in and the out, and I have calculated the idle time for B, C, D, and E here. Okay. Now that is not the final idle time. I have to further go ahead and do some other calculations as well. Now look at the first job. The in for the first job on machine number A will be 0. Okay. The processing time for job number 1 on machine A is given as 7 hours. So 0 plus 7 gives me the value 7, which is the out of the first machine A. Okay. The out of the first machine will be the in for the second machine. That's why 7 is coming here. Clear? 7 plus the processing time, 5 gives you 12. 12 will be the in for machine number C. 12 plus 2, which is the processing time for job number 1 on C, gives you 14, which is again the in for D. And finally, 17 is the in for E. Okay. How did we calculate the idle time? When machine A is processing the first job, B is free. Okay, it's idle. And that's why for 7 hours, machine B is idle. When A and B, both the job number 1 is getting processed on A and B, the total time for C will be 12. Processing or idle time will be 12, right? And similarly for D, it will be 14, and for E, it will be 17. I hope the first row is clear. Now look at the second row and pay attention to this one, because if you understand this, you can solve all the problems. Now the out of the first job will be the in of the second job on machine A. So out is 7 here. So in for the second job, that is job number 3, is 7. Okay, 7 plus its processing time on machine number A gives you 12. Now look at this value. Okay, that means this job number 3 can get processed on machine number B after it is completing the processing on A. Here out is 12, and here for machine number A also, job number 3, out is also 12. Both are same. So this in will be 12. That means machine number B gets free at the same time when the second job is arriving. Okay. Now, what about this one? Here, machine number C, okay, processes job number 1 and completes in 14 hours. After 14 hours, you can say. Whereas it is waiting for the other job to come, because the other job is still getting processed on machine number B. So the maximum of 16 and 14 is 16, and that is what will be the in for machine number C here. Okay, and the difference between 16 and 14, that is 16 minus 14, that is 2, will be my idle time for machine number C. Clear? Again, look at this value. The second job, that is job number 3, gets over on machine C in 21 hours. Okay, and D is already completed his previous job and waiting for the next job. So maximum is between 21 and 17 is 21. So the in will be 21. 21 minus 17, that is 4, will be my idle time for D. And similarly here, between 27 and 26, 27 is the maximum. So in for E, for job number 3, will be 27. Okay, and the difference between these two is 1. So 1 is the 1 hour will be the idle time for E. Similarly, you go ahead and do the calculation for the rest of the 2 jobs. Any doubts in this? Any explanation required?
No, sir.
Great. Okay. Next, what you do is you do the calculation, the total, find out the total of the idle time for each machine here. Now, this is not the final answer. Okay. What is the elapsed time? The total elapsed time? The last processing time gets over, the job gets over on machine number E after 51 hours. Okay. So total elapsed time will be 51 hours. Okay. Clear. Now, what about the idle time on machine number A? Anyone? We have done put a column for A. What is the idle time for A? Anyone? You can post it in the chat. Okay, try to understand this now. Now, once the machine number A completes the last job, that is job number 4, at 26 hours, it is going to sit idle till 51 hours. So 51 minus 26, that will be the idle time for A. That is coming to how many hours? 25 hours. Okay, someone is giving the answer here. So if I change this, 25 hours. What about B? We already have some hours here, 11. And again, once it completes the last job at 29, so 51 minus 29 gives you 22. So 11 plus 22 is 33. So machine number B, or machine B, is idle for 33 hours. Similar calculation you can do for C. 51 minus 32 gives you 19, and this total was 18. So 18 plus 19 gives you 37. For D, again, 51 minus 35 gives you 16. 16 plus 19 gives you 35. And finally, for the last one, we have 18 hours. Any doubts? Okay, Advaith had given the answer 25. Great, Advaith. Any doubts in this problem, guys? Okay, if there is no problem, this is the final answer for the sequencing problem where we are processing n jobs on m machines. Okay, please remember all the steps. Definitely there will be some question on processing time or processing sequencing problem. Okay. Now, as I told you, this will be my last session on DS. If you have any doubts, you can ask me any topic which you want me to discuss or explain you further with different examples might be, you know. Sometimes what happens, you have understood how to process a particular problem. But if the problem is given in words, it becomes difficult to understand. So interpreting the problem given is more important. In some cases, you get the values directly. In some cases, you have to prepare the matrix and then solve it. Okay. So preparing the matrix is the most important part in solving such type of a problem. Where, numbers are not given, only, sentences are given. And you have to work out the payoff matrix or might be some time or something like that. Okay. And try to understand the problem first before you actually jump into solving the problem, because you might be feeling sequencing problem is very easy now. Okay, but if I do not give you the processing times and ask you to create the processing times through some word problem, okay, then you will find that it is difficult. So I will give you some problems to solve where you'll find that there's some twists and turns in the given problem, more tricky to solve it. And might be on Monday, you'll be having a test. So I'll put a message on the group about the assessment. Let me prepare first of all, the MCQ. The first test will be on MCQ based on all the 5 units. Okay, so please prepare on all the 5 units. And the date I'm telling you is Monday. So coming Monday, we'll be having a MCQ test of 10 marks. Or might be 20 as well. Depends on how many questions do I get. And again, I'll post that in the group as well. Today is Wednesday, so you have enough time to study. Okay.